Operating system processes. A process, the active form of a program in execution, progresses sequentially. Programs are passive entities stored on disk as executable files, only becoming processes when loaded into memory. Programs can be initiated through various means like GUI mouse clicks or command line entries. It's possible for one program to manifest as multiple processes, particularly when multiple users execute the same program simultaneously. The process state undergoes several transitions as it executes. Initially, it starts in the new state as it's being created. Once it begins executing instructions, it enters the running state. If it needs to wait for an event, it shifts to the waiting state. In the ready state, the process awaits assignment to a processor, and finally, when execution completes, it enters the terminated state. A process control block is a crucial data structure containing essential information for each process in an operating system. This includes the process state, such as running or waiting, the program counter indicating the location of the next instruction to execute, CPU registers holding process-centric data, CPU scheduling details like priorities and queue pointers, memory management specifics including allocated memory, accounting data such as CPU usage and elapsed clock time since start, and I/O status information like allocated I/O devices and open file lists. A thread, the smallest processing unit in an operating system, typically operates within a process, allowing a single process to host multiple threads. Threads enable concurrent execution within a process, enhancing efficiency and responsiveness. Additionally, I/O status information includes details such as allocated I/O devices for a process and a list of open files, crucial for managing input and output operations effectively within the system. Process scheduling, a critical function of the process manager, involves removing the currently running process from the CPU and selecting the next process based on a specific strategy. It is a fundamental component of multi-programming operating systems, facilitating efficient utilization of resources by managing the allocation of CPU time among multiple processes. Process scheduling, a crucial task for operating systems, manages processes in various states such as ready, waiting, and running. It facilitates the allocation of CPU execution time intervals for each process, aiming to maximize CPU utilization by swiftly switching processes onto the CPU for time sharing, thereby ensuring continuous CPU engagement. Process scheduling queues play a pivotal role by organizing distinct queues for different process states and their corresponding process control blocks. These queues include the job queue, consisting of all processes in the system, the ready queue, housing processes in main memory ready and waiting to execute, and device queues, accommodating processes awaiting I/O device access. Process schedulers, essential components of operating systems, can be categorized into three main types: short-term, long-term, and medium-term. The short-term scheduler, also known as the CPU scheduler, plays a crucial role in selecting the next process for execution and allocating CPU resources accordingly. Often the primary scheduler in a system, it operates at a high frequency, sometimes as frequently as milliseconds, necessitating swift decision-making to maintain system efficiency. Long-term scheduler, also known as the job scheduler, determines which processes should enter the ready queue, influencing the degree of multi-programming. It operates intermittently, potentially taking seconds or minutes due to its infrequent invocation. Medium-term scheduler plays a crucial role in swapping, facilitating the management of swapped-out processes. Operating system requires mechanisms for managing processes, including creation and termination. Process creation involves the generation of new processes within the system, often initiated by a parent process spawning child processes, leading to the formation of a process tree. Each process is typically identified and managed through a unique process identifier, PID. Process termination signifies the end of a process's execution within the system. Process creation in Unix-like systems involves the use of the fork function where a parent process generates a child process. Each child process has only one parent, while a parent process can have multiple children. Various events, such as user requests, system initialization, and batch job initialization, trigger the creation of processes. Process creation in Unix involves two key system calls, fork and exec. The fork system call generates a new process, essentially creating a copy of the current process. Subsequently, the exec system call is utilized to replace the memory space of this new process with that of a different program, effectively initiating a new program within the same process environment. Process termination involves several steps. First, the process executes its final statement and then requests the operating system to delete it using the exit system call. During this termination, status data is returned from the child to the parent through the wait system call. The operating system then deallocates the resources associated with the process. Additionally, the parent has the capability to terminate the execution of its child processes using the abort system call if needed. In the context of process termination in operating systems, certain systems enforce a rule where if a parent process ends, its child processes are also terminated. This principle, known as cascading termination, ensures that not only the direct children but also their descendants are terminated. To manage this, parent processes can utilize the wait system call to pause execution until a child process terminates, allowing for coordinated termination sequences. Inter-process communication is a crucial mechanism within operating systems that facilitates communication between different processes. There are two primary types of communication. First, communication between related processes, such as parent and child processes, where one process initiates the interaction. Second, communication between unrelated processes, enabling interaction between two or more distinct processes. Two primary models of IPC exist: message passing and shared memory. In the message passing model, processes communicate by sending and receiving messages through predefined communication channels. On the other hand, the shared memory model allows processes to share a portion of memory, enabling them to read from and write to the same memory locations. Shared memory in inter-process communication allows multiple processes to communicate by accessing a common area of memory. Unlike other forms of IPC, such as message passing, shared memory puts the control of communication in the hands of user processes rather than the operating system. One significant challenge is ensuring synchronization between processes to prevent conflicts when accessing shared memory. Therefore, mechanisms must be implemented to facilitate this synchronization and coordinate actions among user processes. Inter-process communication offers a means for processes to interact and coordinate their activities without relying on shared variables. This communication method employs a message system, allowing processes to exchange information. The IPC facility comprises two fundamental operations: sending messages and receiving messages. These messages can vary in size, accommodating both fixed and variable sizes as needed. Overall, IPC facilitates seamless communication and synchronization between processes within a system. In inter-process communication, IPC, through message passing, processes P and Q must establish a communication link and exchange messages using send-receive operations. This link can be implemented physically through shared memory, hardware buses, or networks, or logically via direct or indirect methods, and synchronous or asynchronous modes. These options provide flexibility and efficiency in facilitating communication between processes. In inter-process communication utilizing direct communication, processes are required to explicitly name each other to communicate. This involves utilizing the send Q message function to send a message to process Q, and the receive P message function to receive a message from process P. Key properties of this communication method include the automatic establishment of links between processes, the existence of exactly one link between each pair of processes, and the possibility of the link being unidirectional but typically bidirectional in nature. In inter-process communication through indirect communication, messages are exchanged via mailboxes, each assigned a unique ID. Processes can communicate only if they have access to the same mailbox. Key features include the establishment of a communication link only when processes share a common mailbox, allowing each pair of processes to potentially share multiple communication links, and the flexibility for these links to be either unidirectional or bidirectional. Inter-process communication buffering involves managing a queue of messages connected to a link, typically implemented in one of three ways: zero capacity, bounded capacity, or unbounded capacity. In zero capacity, no messages are queued, requiring the sender to wait for the receiver. With bounded capacity, there's a finite length of n messages allowed, and the sender waits if the link is full. In unbounded capacity, the queue has an infinite length, ensuring the sender never waits for the receiver. Client-server systems rely on sockets to enable communication between processes, whether they're on the same machine or different ones. These sockets, comprising an IP address and port number, form the backbone of client-server frameworks. However, socket communication operates at a low level, transmitting unstructured byte streams between processes. In client-server systems, communication is facilitated through sockets, which serve as endpoints for data exchange. A socket is identified by concatenating an IP address and a port number, with the latter distinguishing network services on a host. Communication occurs between pairs of sockets, and ports below 1024 are reserved for well-known, standard services. In client-server systems, communication between processes is facilitated by pipes, which serve as conduits for data exchange. There are two main types: ordinary pipes and named pipes. Ordinary pipes enable one-way communication, requiring the use of two pipes for bidirectional communication. They are limited to communication within the process that created them, often utilized between a parent process and its child. Named pipes, on the other hand, allow access without a strict parent-child relationship, offering more flexibility in communication within the system. Ordinary pipes facilitate communication between processes in a standard producer-consumer manner. In this setup, the producer writes data to one end of the pipe, the write end, while the consumer reads from the other end, the read end, making the communication unidirectional. This mechanism necessitates a parent-child relationship between the communicating processes. Named pipes, available on both Unix and Windows systems, offer enhanced communication capabilities compared to ordinary pipes. They facilitate bidirectional communication without requiring a parent-child relationship between processes, enabling multiple processes to utilize the same named pipe for communication purposes. Thank you for watching.